Okay, looks like that's going through fine. People said they would show up. We'll see what happens. Okay, and we got YouTube going. Got 3 people watching. Hello. We'll be starting soon. Hopefully the video and the audio is good. Let me see. Is Twitch still unhappy about the bit rate? Let's see. Okay, it likes the bit rate now. It's somewhat confusing. Okay, heading back. Okay, piano. Okay, it's 10:30. So welcome everyone. This is FPGA Zealot. We're going to be going over a little side project. I like to spend the Saturdays doing some fun little projects that I have on my to-do list. I have a way too many little side projects I want to try, and one of them is getting the DualShock controller, the version 1, working with like a little FPGA video game, whether it's Doom or something else. We'll figure out how to do it. Now here today we're just going to go through one of the steps along that progress, and that is with this hardware from Devo. Adam Taylor's company. We're looking at we have a Raspberry Pi 240, which is a small little microcontroller connected to a Spartan-7 FPGA, a really small Spartan-7 FPGA, like 3,500 LUTs. But I just wanted to start working on the Raspberry Pi, decoding the DualShock, and then outputting it on the PMODs. And we can look at that a little bit later. But thank you for joining us. Feel free to say hi in the chat. Feel free to ask any questions. It's supposed to be more of a casual one. This isn't sponsored or anything like that. The hardware was a gift from Adam Taylor, but there's no expectation of any like review or content creation for it or anything like that. Let's see any other disclaimers. Oh, social media. So I'm streaming on YouTube, Twitch, and LinkedIn. Maybe we'll stream on other um, systems or other services later. But you can also find me on X, where I try to post a little bit. I am curious. You can also find me on LinkedIn as Andrew Wilson. Okay, so disclaimers, this is not a sponsored live stream. This isn't just personal project. I am not employed by AMD or Adam Taylor's Group or anything like that. I don't offer any official support for these products. The content on this channel is created for informational purposes only. I'm looking at fun little hobby projects. It's kind of related to retro gaming. I'm kind of looking at some of the low-level systems for what would go into like maybe retro gaming or designing a game custom on an FPGA. All the opinions expressed on this channel are my own. And so here's the hardware we're using. It's hooked up right now, so I can't really like show it in front of the camera. But we have 4 PMODs. One is connected to the Raspberry Pi. 3 are connected to the Spartan-7, but one of them is missing the connecting resistors, so it's not hooked up correctly. So we only have 3 PMODs, one for the Raspberry Pi 240 microcontroller and 2 for the FPGA. And I have it set up as this, right? So we have the Raspberry Pi has a little PMOD connector connecting to a DualShock controller. This is probably a cheap knockoff, not an original DualShock. I'll probably look at maybe getting a nicer DualShock. And then we have the dual PMOD to DVI over HDMI connector. This is an Icebreaker product. I have the website open, so we can pop that open right here. So we're using this guy that you can buy at 1BitSpace. Sold out for the moment. But this is just kind of the basic little 12-bit system. I found this to be a very useful little cheap video. I can do 1080p 60 frames per second pretty well on it. So we'll look at that. I wonder if we could do a hyper RAM on the other one. Do like a single hyper RAM. These are just duals. That would be interesting if we shared that Raspberry Pi, but that would be silly. Okay. Yeah, back to our little slides. So, like we said, we're going to have the DualShock controller connected to the Raspberry Pi 240, and then we're going to have the video connected to, I think, mod 0 and 1 on the FPGA. So, to start with, we're going to start with the Raspberry Pi controls. So going here, so you get the DualShock controller over here. So we have a basic DualShock controller. And we want to connect it to the Raspberry Pi 240. This is using a SPI interface. There's a few, if you Google it, you can get some interesting information. It's a rather simple system. You just kind of send out a pull request. See if they have it explained in this one. To do where you are sending out a pull request. Okay. It's explained better in this Hackster IO project, where he talks about doing a polling command, and you get the buttons and you get the axes. So this is basically what we're doing. We're just doing a basic SPI interface. We get the ID of the states, and we get the ACK right here. It's the 5A. I believe that he explained that somewhere. It's some sort of ACK. And then you just get the next 6 bytes, right, contain all the information you need. And you can also send a rumble command to it, which is interesting. Try that. I don't think mine has rumble. If you have a fancy DualShock, which I should probably look into getting the button pressure, that would be really interesting to see the button pressure on each of these. That might be something cool. Might look at trying to get a DualShock 2 to look at pressure activation. But this is basically the command here, and we're just going to hook that up to the system. The issue is, so the Raspberry Pi 240 does come with SPI subsystems. Like right here we have 2 SPI peripherals, but those are kind of hard coded to certain pins. So we go down to this GPIO function table. The SPI, TX, RX, chip select, and the clock, they're all fixed to very specific pins. And unfortunately, the way this PMOD is set up, and the controller is wired, we can't take advantage of this system, right? So we can't. I didn't want to rewire trying to get the SPI controller working. So I ended up having to do bit bang. So instead of using a dedicated SPI controller, we're just going to bit bang it in the Raspberry Pi, which is not that bad. It really isn't that bad of processing, at least by itself. I don't know how the bit bang would go in the future. Maybe we need to use a PIO to offset some of that, but right now it's not a lot of processing. But if we go to the schematic, we are stuck on pins 10, 11, 12, and 13. And the pins I'm using is 12 for clock, 11 for output, 13 for input, and chip select is on 10. But if we go to here, we go 10. 10 is clock, not chip select. So these are all kind of off. And even if we try to go to the next 4 pins on the data sheet, which is GPIO 14 to 17, 14 to 17 are kind of routed the same way, and so there's like switching to controller 1 or controller 2 won't help. We would have to actually rewire it. Maybe when I go to the actual system, I can try to rewire it and get it working in a real system. I have we could do little jumper wires to get it up and running, but for now we're just going to bit bang it. Let me show you the bit bang software. Looking at here. So the bit bang software, it's sleeping here. So you're basically when we transfer bytes, we are transferring bit by bit. We set the clock, we sleep, we set the values and whatnot. So that's transferring a byte. Just transferring 9 bytes. And there's the TX and the RX, right? So that's just your basic hand-to-hand SPI. Where's the chip select being set up? Select. Okay, transfer 9, we're doing low there. Okay, so you have to do chip select out of the transfer byte. And then we're going to read the values. We're expecting the ACK on byte 3 of the receive side. And then this is just a simple parser that's parsing out values. And the pressed bits, doing a very slow form of that, especially when I repackage it. I should just have it transmit the raw stuff. So I need to put to do here. Do. Now we'll put that to do up here. To do. Transfer raw button byte for FPGA. So yeah, we're doing this process of filtering it, and then we just send the raw data to the FPGA anyway. So there's no need to really do this. We can probably have a like read formatted. But okay, let's go ahead and show you how this works on the hardware. So we're just going to do DualShock system. Yeah, here we go. So following the schematic, the pinout, the controllers, the PMOD, and the schematic, these are our pins, like we said before. We're going to have the I guess the sample frequency going to be 40 kilohertz. And we're going to look for buttons. So, I mean, not terribly hard. Much easier setting it up on the Raspberry Pi 250 with Python instead of trying to do other systems. Okay, so you can go ahead and run this. So in the bottom corner here, we have the state of the Raspberry Pi 240. And YouTube, yeah. Good morning as well. Julius, good morning. So we're going to be, we have where are we starting? We're starting here. We have the cross, the circle, the triangle, the square, start, select, and we have the D-pad arrow keys. We have the triggers. Analog mode's on, that's why. We have the triggers. Oh yeah, I have to hit the button so I update that. And we have the stick pushes, and then we have the movement of the XY for left and right. So the controller works. It's great. And let's see, the ID should change. Yeah, the ID changed to 41 for normal mode. Then this is analog mode. And those are our raw inputs for the controller. Cool. So Raspberry Pi communication controller over SPI, super easy, especially even if we bit bank it. It doesn't take much code. to set up the bit paying and get that working. So now we need to send this to the FPGA. We're going to use the same PIO interface that we used before and have the microblaze 5 on the FPGA parse that data. Right now it's just going to be passing that through to the subsystem, but nothing more complicated. Okay, open the project. It's opening. I'll bring it over in a second. Okay. So we got going back to the slides. We've done the Raspberry Pi communicating with the DualShock controller using SPI. Now we're going to look at the FPGA image that we have set up in the block diagram. Oh, I need to go figure out what's causing the timing issues. So we have the Raspberry Pi 240 signal coming in, going into our data 5.0. It's going into the processor. Then the processor is sending that over the AXI data port to a AXI interconnect, which is then connected to a GPIO. We're just going to do a basic GPIO. And then we have the VGA core. So we're going to probably spend some time into the VGA core. This is the example code for the icebreaker. Let me see if I can find, where's the PMod repository? Is it? Yeah, so DVI 12-bit, we go to whatever version we want, and where is the, where did they put the VGA core? Sitting in the 24-bit? No, these are, we want examples, not so let's go back to Icebreaker FPGA. We want Icebreaker Verilog examples. Going here, 12-bit. Okay, here's the VGA core. So this is where the file that we modified. And we only kind of do two modifications to this system. So in the VGA core and the timing core. So the first thing we did in the VGA timing core is this is set up for different resolutions, right? That it talks about here, and the default is 80 by 60 for 60 frames per second. We're going to go 1080p 60 frames per second. So we set up the H-sync and the V-sync parameters to be able to do 1080p correctly. That's set up. Then in the VGA core, I took the test pattern mode. So there's like this down here. So there's like a test pattern mode, and it normally produces just like, your test lines, whatever. And I just replaced it with a little controller. ChatGPT helped with the rectangles, so it's a bunch of rectangles. We just placed a bunch of rectangles around the system for the different buttons and the sticks and whatnot. And then we just created a bunch of you call continuous assignment or concurrent logic, not sequential logic, of taking the XY parameter of the resolution and comparing that with the various constraints for the different button locations and sizes. We can show this off real quick and program it so you guys can see it. Then we can talk about the code to program it. But in the end, we are just sending the buttons in right here. So we have the button locations, and then right here we have the stick axes that we're going to look at. I'm a little curious of what we are failing in timing, so I'm going to jump into the timing graph to see if we want to try to rebuild this before we run it. And second. Yeah. Does anyone else have any small FPGA projects that they're interested about? Do you get the chance to play with like little FPGA projects like this? Are you more I guess working on industry level I would say FPGA designs? Um it's hard to be able to play around with some of these smaller interfaces. When at work it's much more focused on more advanced high bandwidth interfaces. Okay, back to timing. I want to see what that was. We have 204 endpoints failing. Oh, is this? I bet I know what this is. This is, okay, the axes. We're going through a bunch of logic. So we might want to, it's okay because it should settle. It shouldn't be a big issue. But we should probably look at putting some logic flops in here so that we're not doing the logic in a single cycle. How bad? It's only not that bad. Total delay is 9. The requirement is 6. So it'd be good to put some flip flops in here for this logic, so that we can do this logic separately. Um, I figure out where this is in code. This is going directly to the output. Yeah, okay. So this is, oh, that's the green color. So that's going to be, so basically these guys right here, we need to break these down into separate functions and pipeline it. I'll have to do that sometime. That'll be a to do to look at. Um, we want to pipeline logic. Not a big deal. We're not going to see any major glitching. The data is going to settle. Flip flops not get into a bad state. Okay, I'll have to pipeline that logic. Okay, that makes sense. Let's going back here. Utilization. I want to look at utilization and then we can run it on the system. So let's go report utilization. So in the report utilization, how much we're using on the FPGA, we're using quite a bit. We probably could run the microblaze in a smaller mode, in all honesty. I do wonder, like, if we pop over to the diagram here, can we optimize this for size? Current settings. Go here, select, yeah, area. I don't know if we can get any smaller. We might be able to turn off. Don't need code compression. Actually, code compression would be good. Optimize standard none. Floating point none. Yeah. I don't know. Maybe I'll look at making that much smaller and fixing the pipelining. Outdate, but that's okay. So let's go program it and show you what the screen looks like, and then we can get the code up and running. So let's go ahead, open the target. So we still have the controller working on the Raspberry Pi, right? So we can control it. But let's see what the GUI on the FPGA is. Okay, open it. Auto. Actually, I should just be able to open this. I should be able to add this as a stream. Gonna be the game capture. Now, I guess we're going to add video capture device. El Gato. Okay. And I found it. Cool. We'll hit OK and make it really small. Okay. Maybe we can. So let me see. Okay. So that's our controller. Let me see. We can put some offsets on it. Top left. Okay. Oh, we did 200 there. Right. 200. Top. We do 200. Bottom. 200. Yeah, sure. There's the controller up there. Cool. So the graphics working, but we don't have communication. So we want to send the data. So going back to the diagram, we want to send the data over our little parallel bus with the Raspberry Pi, which is right here. So we need to set up the microblaze. So we're going to go look at the Vitus. I already have this set up, so we can do this quickly. And then we can run the code to send the Raspberry Pi code to it. Let's say, yeah, what I'm going to do. And I want to open this. Okay, this is the guy we want to look at. So in this code, we're just providing, we're going to be sending over a sync word, the buttons, and the axes controller. So we're going to do the 16 bits for the buttons and the 32 bits for the axes. And we're going to send that over at about 50 hertz. That's what the Raspberry Pi is going to be doing. We're using the PIO that we looked at last time. So feel free to look at the previous video to see how that PIO system works. Then Vitus, in our Hello World system, go to check out our Hello World C program. And it's very basic. We're using the sync word, deadbeef. This is the GPIO addresses. So there's GPIO output 1, GPIO output 2, and we're basically going to wait for the sync word, and then we're going to use the next two words for buttons and axes, and then we're just going to write those to these pointers, and that's all we're really doing on our system. So let's get this. Let's show you how to set up the JTAG output on the microblaze controller. Okay, so for setting up the JPEG output on the microcontroller, we're going to open XSDB. We're going to type in connect. We'll look at our targets. And we're going to look target 3, right? Now we do targets again. We see the 3's highlighted. We're just going to do JTAG terminal. And then we'll have another window pop up over here. This is going to be our system. So if I hit run here, and then I pop over here, we should see eventually a little like DualShock controller is ready to go. Right there. Okay, so DualShock controller is receive starting. I turned off the UART because it's slow. Then that's really all we're going to see there. And then over on the Thorny side, we can begin doing the controller. So here, and let me bring up this a little bit. Right, we have our state. And you can see in our little video capture up here that we have our controllers. Okay, can't really get like a down screen or something, right? Up arrow, left arrow, right arrow, down arrow, boom, control buttons, start, select, trigger, 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 button click, and then we can move the sticks around. And it's pretty good latency. I mean, like, feels like it's turning on pretty quickly, which is good because it's going from here through the Raspberry Pi, through the FPGA, through the video capture device, and whatnot. So I think it's doing pretty good latency, especially when I'm looking at the preview of the OBS tool to see it work. Pretty good latency, pretty good responsiveness. So that was the little project to get it running. I mean, we can go. I'm not sure if anyone has any questions. If you do have questions later in watching the VOD, um, these other interfaces are for the kind of the test modes that are supported by the VGA core in a reset. And then we're just splitting up the display port into red, green, and blue. And then we just need to map out all the constraints for the various different Pmon connections, which are active, HSync, VSync, the blue colors, the green colors, and the red colors for 12-bit color. We do have a divide clock, and we do have a system clock. The DVI clock is an output, I believe. Diagram, yeah, it's an output. And then this is a system clock. We are running at like 140 megahertz, I believe. Where's my clock? Clock wizard. Where's my clock wizard? Here's my clock wizard. You can go look at the output frequency. So we're running at 148.5, and bring up Elgato. It's not gonna be happy. I might have to. We're gonna have to disable that. Bring up Elgato Studio so you can see it up. Device is already in use. Okay, well, it's 1080p, 60 frames per second. I'm gonna have to like turn off the OBS capture. But we're getting good resolution, good frequency, good latency response from the system. And that's kind of what I wanted to walk through today, is being able to do this type of communication between Raspberry Pi 240 and a microblaze. So this is kind of the beginning. So I kind of talk a little bit about what I want to try to do next, and I'll probably post some updates in my Discord and social media post. I use this as a fidget toy. Interesting. My camera is picking this up very well. My arm mic, you're filtering this noise out. That's good. Okay, so what we're doing right now, does use a majority of the system, right? Summary wise, we're using almost 80% of the LUTs and 80% of the VRAMs. So what else can we really do here? And my goal is to turn this FPGA into a frame buffer for the Raspberry Pi 240. It would take probably a lot of I mean, maybe not too much of the PIO, but the FPGA would provide a consistent frame buffer that you could kind of reduce a lot of the functionality on the Raspberry Pi 240. So I want to run video games and use the FPGA as kind of a dedicated frame buffer and maybe some other little accelerations. So I want to get a frame buffer working. To get the frame buffer working on this hardware, though, we're going to have to use the SRAM. Where's the SRAM? Right here. So this RAM device right here. Yeah, we can go find it. Yeah, we have a 64 megabit RAM that I want to use as a frame buffer. And if we're doing 1080p frames, so let's see. So we're doing 1080 times 1920. That's how many pixels are in a single frame. And we want what we're doing 12-bit, so we do times that by 12. That's 24 megabits. So we would need 24 megabits to do one frame. So we might want to reduce the resolution down a bit. So I mean, if we did 6 times 80 times 12, that's only 5 megabit per frame. So I mean, we could try doing a basic frame buffer, but I think it'd be interesting to set up a frame buffer inside the FPGA and then send communication and have the microblaze act as kind of like a video coprocessor to the Raspberry Pi that would be running the game and the controller setup. So I'll be looking at what some fun games we can do. I can set up on it. I did find Doom running on the RP2040, so I might be able to set this up and scale it up to be better. Okay, yeah. Julie, she has some questions pop up. So the PS controller, yep, this PS controller is connected to the Raspberry Pi 240. So this is the Raspberry Pi 2. The Raspberry Pi microcontroller is handling the SPI interface, the direct connection for this, and the frame buffer allows us to have continuous video without any processing. So the idea of using a frame buffer is that the video is continuing running and the processors don't have to maintain it. They can focus on games or sprites or something like that. And the idea is that you would have multiple frame buffers and you would finish one frame, switch which frame you're referencing, and then work on the next frame. So the processor would work on the next frame with like sprites or something, and then we could jump on to the next one while it's being displayed, so that we can do that. So I don't know how the Doom game is set up, how we can potentially like set up sprites or video output on the other side, but it will reduce the functionality so we can support a high refresh rate, but the or not refresh rate, that the video will be a consistent frame rate while the game can run at its own computational frame rate. Otherwise, we basically have to have PIOs and DMA consistently trying to work in the Raspberry Pi to do video. But in this situation, we're just going to let the FPGA handle it. I am curious, they do have a solution here about how they did the rendering. So yeah, we want to do a double buffer display. Double buffered mode. So we're creating a frame and showing a frame. So yeah, this would be a really good project to work out with the Raspberry Pi into an FPGA and try to split the functionality and then set up a control for it. Let's see if we can find the display. And that's okay, we want the source. Source. I don't even know. Is there like PIO setup in here? We can like figure out where the PIO. Oh, the iVideo.c video Doom. Yeah, so it'll be interesting to walk through this write up and split up the functionality between the FPGA and other systems. But yeah, it'd be a fun little project to work with some of those smaller issues. So that's mostly what we had today. I'll probably be looking at more technical details and some of the side projects in the future before we jump back to this. But next week we have a Thursday Altera simulation demo. Saturday, I think I want to do an Altera DDR controller setup and look at the different DDR controllers in the Agile X5 and how you configure them and test them and calibrate them. And then we'll probably go back to AMD Advent of Code HLS, or maybe DMA Interrupt or DMA Scatter Gather. Data movers. AMD data movers. I think I'll do that on the next stream. Okay. Okay, so Julius, you have a great question. YouTube, will it run on the microBlaze processor? Will receive input from the PS controller, perform processing, and output video? So the goal is I want to split functionality between the Raspberry Pi 240 and the microprocessor in the FPGA. I guess it's going to be a challenge. What is the best way to split software between the RP2040 and the FPGA microBlaze feed? I want to find out. So we're just kind of going to be exploring between the Raspberry Pi 240 and the FPGA and split it apart. Well, interesting, that came back to me. That's going to be mostly the setup. Okay. Grab that, bring that down here. It's super small right here. So that's going to be the end for the stream. If you have any questions, feel free to post them now or in the chat or comments later. You can also join the Discord. Feel free to leave a like or a subscription or a repost or whatever, on YouTube, X, Twitch, or LinkedIn. Thank you for joining us. This was supposed to be more of a casual stream, so we'll probably do more intense FPGA implementations in future videos. But thank you for your time. Major leagues there. I'm gonna have fun doing the controller as like a fidget. This controller is gonna be my little fidget toy for a while. I'll just leave the capture on the screen. Okay. Well, thanks everyone. Feel free to join next week, later next year. We'll see what else we can bring up in some of these demonstrations. I look for any suggestions or questions, so feel free. Once again, Discord, comments, whatever. Leave your feedback. I want to be able to make this an enjoyable experience for everyone, that they can learn about FPGAs and how to be able to use them in hobby projects, startups, industry, and research. And hope to hit all those topics with various different videos. But I think that's going to be it for today. So I will see you next week. Goodbye.